Hello my friends and welcome back to the You Can Do TV channel. Cement is manufactured by thermally treating a mineral mixture of limestone, sandstone and shale, with some minor raw materials. In today's video, we will visit Lafarge Exshaw cement plant to explore the process of cement production here. The cement manufacturing process begins with the extraction of limestone from a world-class limestone deposit. The limestone is drilled, blasted, and then transported to the crushing system where it is crushed down to a 3/4- rock. Shales and sandstones are added to produce what's known as a pre-homogenized mix. The pre-homogenized mix is then further refined into a raw mix and taken to the grind stage where it is ground into a fine powder. The raw materials are ground in a vertical roller mill and the recipe is checked to ensure the correct proportions of limestone, iron, silica, and alumina. The next stage is the preheater tower, where the ground raw material enters at the top of the tower and is preheated all the way to about 900 degrees Celsius through a series of cyclones. At the bottom of the tower, the material enters the rotary kiln, which is the heart of the manufacturing process. The material is heated up to 1450 degrees Celsius and the chemical reactions occur, turning the raw materials into the main component of cement, which is clinker. The clinker is then cooled down and ground with other additives such as gypsum to produce the fine powder that we call cement. U.S. Concrete's Precast facility in San Diego is one of 7 in the company's Precast division. The production crew at the San Diego plant usually starts work at 6 a.m. as flow has been predetermined already by weeks of planning ahead, and there's a lot of on-tarping, stripping, and unbolting. Smaller products such as drain boxes, catch basins, and meter boxes are stripped and laid on dunnage awaiting transport to either a delivery vehicle or the yard. Utility vaults as large as 40 tons are stripped and flipped on the eastern end of the plant. Once all products are stripped, workers begin prepping the forms, including cleaning, caulking, and applying form oil. Meanwhile, on the western end of the plant, the weld shop is busy preparing cages for the empty forms. Large vault cages are assembled upside down on a raised platform by a welder using pre-bent rebar. A cage for a large vault can take several hours. Over by the state-of-the-art batch plant, the morning begins with daily preparations in anticipation of the first batch, which usually occurs around 9 a.m. Once details are entered into the computer, the automated batch plant comes to life. Outside bins release the specified amount of fine and coarse aggregate, taking into account moisture content. The aggregate falls to a conveyor belt, which transfers it into one of two hoppers. The ingredients are mixed, and the batch plant adds water, admixtures, color, and fiber as needed. Workers then place a bucket under one of two shoes, and the bucket is moved by forklift to the overhead cranes and taken to the part of the plant that needs it. The plant produces a wide variety of standard precast products, including site furnishings, underground utility solutions, and wastewater solutions. These products are stripped and laid on dunnage for delivery or storage in the yard. Throughout the manufacturing process, the plant has a quality control team that monitors the quality of the materials, the mixing process, the casting process, and the finished precast elements. Any defects or issues are identified and addressed promptly to ensure that the finished product meets the required standards and specifications. Aluminum alloy formwork systems have emerged as a revolutionary solution in the construction industry, reshaping the landscape of building practices globally. With the society advancing and the construction industry booming in various parts of the world, the adoption of aluminum alloy formwork systems has gained significant traction. This innovative construction technology, widely utilized in developed countries like Europe and America, has also found favor among contractors in emerging economies such as Mexico, Brazil, Malaysia, Korea, India, and notably in China, where the construction industry is experiencing exponential growth. The application of aluminum alloy formwork systems is widespread, particularly in high-rise building projects across different cities including Hong Kong, Macau, Guangzhou, Changsha, and many others. Advantages of aluminum alloy formwork systems. Short construction period. One of the most significant advantages of aluminum alloy formwork systems is their ability to expedite the construction process. With efficient assembly and quick installation, these systems enable shorter construction cycles, resulting in faster project completion times compared to conventional methods. Easy assembly. Aluminum alloy formwork systems are designed for ease of assembly, requiring minimal specialized labor. Skilled workers can swiftly install formworks covering large areas each day, significantly enhancing productivity on construction sites. Firm and reusable structure. The inherent strength and durability of aluminum alloy formwork systems ensure a stable structure throughout the construction process. Moreover, these systems are reusable, with recycling times exceeding 200 cycles. This reusability factor not only reduces material waste but also contributes to cost savings in the long run. Labor cost savings. By streamlining the construction process and minimizing the need for manual labor, aluminum alloy formwork systems help reduce labor costs significantly. Skilled workers can efficiently install and dismantle formworks, optimizing resource allocation and improving project profitability. Environmental sustainability. Aluminum alloy formwork systems offer a sustainable alternative to traditional construction methods by minimizing environmental impact. The elimination of iron nails and reduction in construction waste contribute to a cleaner, greener construction environment, aligning with sustainable development goals. Installation process of aluminum alloy formwork systems. Preparation. Before the installation process begins, thorough planning and preparation are essential. This includes assessing project requirements, determining the layout of formworks, and ensuring the availability of necessary materials and equipment. Assembly of formwork components. The installation process commences with the assembly of formwork components, including panels, beams, props, and connectors. These components are carefully aligned and interconnected according to the desired structure and dimensions of the building. Install slab panel. The formwork panels are aligned and interconnected to form the desired slab shape and dimensions. Skilled workers meticulously position the panels, ensuring proper alignment and support. Once in place, the panels are securely fixed using connectors and braces to prevent any movement during concrete pouring. Install staircase. The formwork panels are configured to create the shape and dimensions of the staircase, taking into account factors such as riser height, tread width, and overall dimensions. Once assembled, the staircase formwork is securely fixed in place using connectors and braces. Install next the support beams. Support beams play a crucial role in providing structural support and stability to the building framework. The beams are securely fixed using connectors and supports, ensuring stability during construction and after completion. Double track confirmation. Double track confirmation is a quality control measure employed during the installation process to ensure accuracy and precision. This redundant verification process helps detect any discrepancies or errors, allowing for timely corrections and adjustments. Installation on the cartridge. Installation on the cartridge refers to mounting or fixing components onto a cartridge or support structure. Proper installation on the cartridge ensures stability, support, and alignment of the formwork system during construction activities such as concrete pouring or structural assembly. Installation kicker plate fixing screws. Kicker plates are used to support and align formwork panels, particularly at the bottom or edges of vertical formwork elements such as walls or columns. Installing kicker plate fixing screws involves securely fastening the kicker plates to the formwork panels using screws or bolts. Fixing and alignment. Once the formwork components are assembled, they are fixed and aligned to ensure structural integrity and dimensional accuracy. Skilled workers utilize precision tools and techniques to ensure proper alignment and stability of the formwork system. Grouting and concrete pouring. After the formwork is securely in place, the next step involves grouting and concrete pouring. High-quality concrete is mixed and poured into the formwork, filling the mold and shaping the desired structure. Curing and removal of formwork. Following concrete pouring, the curing process begins to allow the concrete to achieve optimal strength and durability. Once the concrete has cured sufficiently, the formwork can be removed. Due to the efficiency of aluminum alloy formwork systems, formwork removal can typically occur within 24 to 36 hours after concrete pouring. Reuse and recycling. After the completion of one phase of construction, the aluminum alloy formwork components can be dismantled, cleaned, and prepared for reuse in subsequent phases or projects. With proper maintenance and care, These components can undergo multiple recycling cycles, maximizing their lifespan and economic value. In the realm of construction, innovation is the cornerstone of progress. The advent of insulated panels has historically been confined to commercial projects until now. Bondor, in collaboration with BlueScope Steel and Dulux Acratex, has pioneered a groundbreaking solution for residential applications: Insul structural wall. This all-in-one structural insulated wall panel presents a paradigm shift in building technology, offering a viable alternative to traditional monolithic construction methods. Let's delve deeper into the features, advantages, typical applications, and installation process of Insul wall. Features and advantages. Insul wall boasts a plethora of features designed to enhance efficiency, durability, and versatility in residential and commercial settings. Ready-made for finishing. With a unique prime-coated BlueScope steel technology, Insul wall comes prepared for various finishing options including painting, rendering, or cladding, providing flexibility in aesthetic choices. Preformed rebated joint. The panel incorporates a preformed rebated joint, facilitating seamless plaster setting for a continuous coated surface, ensuring a sleek and polished interior finish. Electrical service ducts. Simplifying the roughing and process of electrical wiring, Insul wall integrates electrical service ducts, streamlining installation and reducing labor costs. Alternative building solution. Insul wall offers an alternative to conventional building methods, replacing multiple layers and trades with a single, integrated solution. This not only accelerates construction timelines but also minimizes material waste and environmental impact. Typical applications. Insul wall finds its utility across various construction projects, including but not limited to residential, ideal for both new construction and renovations. Insul wall enhances energy efficiency and thermal comfort in homes while providing a sleek and modern finish. Modular buildings. Suited for prefabricated modular constructions, Insul wall offers rapid assembly and structural integrity, making it an excellent choice for off-site manufacturing. Commercial. From office complexes to retail spaces, Insul wall delivers superior insulation properties and aesthetic appeal, meeting the demands of modern commercial construction. Insul wall is a lightweight yet structurally robust panel composed of EPS-FR, expanded polystyrene with fire-retardant core, enveloped in 0.6 mm G300 prime-coated bluescope steel. Available in thicknesses of 90 mm for interior walls and 140 mm for exterior walls, Insul wall is engineered to meet the stringent requirements of both residential and commercial applications. The installation of Insul wall follows a systematic approach to ensure optimal performance and longevity. Panel handling. Careful handling of panels is essential to prevent damage. Mechanical aids should be employed for lifting and positioning panels, considering their weight and dimensions. Supporting frame. Prior to installation, ensure that the supporting frame is structurally sound and meets the specifications outlined by the engineer. Fixing and flashing. Utilize high-grade carbon steel fasteners and bluescope color bond steel flashings as per the recommended guidelines. Seal all joints and penetrations with appropriate sealants to prevent water ingress and ensure weather tightness. Cutting and trimming. Panels may require cutting and trimming to achieve a flush finish. Use suitable metal cutting tools for precision and accuracy. Finishing touches. Once installed, fill any gaps with sealant or foam filler and remove any debris from the panel surfaces. Follow the recommended maintenance procedures to preserve the integrity of the steel profiles. This video shows the construction of a monolithic protosphere dome, a building system aimed for people living in the Arctic. Before construction begins, the site undergoes preparation to ensure a stable foundation. The construction commences with the creation of a concrete ring beam foundation reinforced with steel rebar. This ring beam provides the structural integrity necessary to withstand various disasters. In some cases, for smaller domes, an integrated floor ring foundation is used. Otherwise, the floor is poured after the completion of the dome. A custom-designed airform made from PVC-coated fabric is attached to the ring beam. This airform is inflated with fans to a specified pressure, usually around 2 inches of water column. It takes the shape of the structure and remains inflated throughout the construction process, serving as a mold for the dome. Approximately 3 inches of polyurethane foam, known for its exceptional insulation properties, is sprayed onto the interior of the airform. Special rebar hangers are embedded into the foam to provide a base for attaching the steel reinforcing bars, rebar. A super strong spray mix of concrete, known as shotcrete, is sprayed onto the interior surface of the dome. The steel rebar is embedded within the concrete to enhance its strength and durability. The thickness of the concrete varies depending on the size and purpose of the building. Once the concrete is set, the troweling process begins to ensure a smooth and uniform finish on the interior surface of the dome. This step adds to the aesthetic appeal of the structure while enhancing its durability. Throughout the construction process, the dome gains strength with each completed step. After the concrete sets and the airform is removed, the dome is left with a single-ply roofing membrane, serving as a vapor barrier and protecting the foam insulation from harsh elements. The monolithic Protosphere dome offers numerous benefits, including energy efficiency, cost-effectiveness, and disaster resistance. These qualities make them ideal for various applications, from homes and schools to sports facilities and churches. Moreover, their longevity and minimal maintenance requirements ensure that they remain functional and reliable for centuries to come, making them a truly futuristic and sustainable building solution. Foam concrete, renowned for its lightweight nature, excellent insulation properties, and versatility, has emerged as a revolutionary material in modern construction. Its application in the construction of a house showcases a streamlined process that optimizes time, resources, and performance. Let's delve into a comprehensive overview of the construction process over 6 days, integrating foam concrete into each step. Day 1. Foundations and infrastructure setup. The construction journey commences with laying the groundwork, both figuratively and literally. On the first day, the focus is on establishing the foundations of the house. Concurrently, the sewerage and water supply systems piping are intricately laid beneath the surface, ensuring a robust infrastructure for the house. These systems are crucial lifelines, demanding precision and expertise during installation. Like any construction method, there are also some disadvantages to consider. Let's explore the characteristics, advantages, and potential drawbacks of foam concrete houses. Advantages of foam concrete houses. Perfect thermal and sound insulation. Foam concrete boasts exceptional thermal and sound insulation properties, surpassing those of conventional bricks. With insulation characteristics 3 times higher than traditional materials, foam concrete ensures comfortable indoor environments year-round. It minimizes heat loss during colder months and reduces heat gain in warmer climates, enhancing energy efficiency and lowering heating and cooling costs. Additionally, its soundproofing capabilities create serene living spaces insulated from external noise, promoting tranquility and comfort within the home. Day 2. Waterproofing and formwork preparation. As the project advances, attention shifts towards safeguarding the structure against moisture ingress. A waterproofing coating is meticulously applied, shielding the building from potential water damage and reinforcing its longevity. Simultaneously, formwork is erected, providing the mold for subsequent concrete pouring. This stage sets the stage for the integration of foam concrete, aligning with the sustainable ethos of the construction process. Ecological sustainability. Foam concrete is hailed as an environmentally friendly material, aligning with sustainable construction practices. Its composition, typically consisting of cement, water, and foam, minimizes environmental impact compared to resource-intensive materials like bricks or concrete blocks. The production process generates fewer carbon emissions and consumes less energy, contributing to a reduced carbon footprint. Moreover, foam concrete is often manufactured using recycled materials, further enhancing its eco-friendly profile. By choosing foam concrete for house construction, homeowners can support green building initiatives and contribute to environmental preservation. Energy savings. The superior thermal insulation provided by foam concrete translates into significant energy savings for homeowners. By minimizing heat transfer through walls and roofs, foam concrete houses require less energy for heating and cooling, resulting in substantial cost savings. Studies have shown that foam concrete can reduce heating and cooling costs by up to 40%, making it an economically viable choice in the long run. The energy efficiency of foam concrete houses not only benefits homeowners financially but also reduces overall energy consumption and dependence on fossil fuels, thereby mitigating environmental impact. Day 3. Walls and partial slab construction ducting of essential infrastructure components, including electricity, water, and sewerage, takes precedence on the third day. With the groundwork laid, the focus shifts towards pouring walls and a portion of the slab with foam concrete. This phase underscores the superior thermal and acoustic insulation properties of foam concrete, enhancing the comfort and energy efficiency of the dwelling. Samples are meticulously taken to ensure quality control and adherence to specifications. Fire resistance. Foam concrete belongs to the category of non-combustible materials, offering inherent fire resistance and enhancing the safety of occupants. In the event of a fire, foam concrete does not contribute to the spread of flames, providing valuable time for evacuation and minimizing property damage. This fire-resistant characteristic adds an extra layer of security and peace of mind for homeowners, ensuring the structural integrity and resilience of foam concrete houses in the face of fire hazards. Day 4. Slab completion and joinery fitting. Continuing the momentum, the cast portion of the slab is laid on the fourth day, marking a significant milestone in the construction timeline. Formwork removal from walls and a section of the slab unveils the structural integrity achieved through meticulous planning and execution. Joinery fitting commences, harmonizing functionality with aesthetics and complementing the architectural vision of the house. Laying of the cast part of the slab. Putting up the formwork for a part of the slab directly on the building. Pouring of a part of the slab with foam concrete. Day 5. Facade, tiling, and painting. As the construction progresses, attention turns towards the exterior aesthetics of the house. The 5th day witnesses the meticulous craftsmanship involved in crafting the facade, epitomizing the fusion of form and function. Tiling work embellishes the interiors, infusing character and style into living spaces. Painting work adds the finishing touches, breathing life into the structure and reflecting the homeowner's personal taste and preferences. Disadvantages of foam concrete houses. Limited load-bearing capacity. One of the primary drawbacks of foam concrete is its relatively low load-bearing capacity compared to traditional building materials like concrete or steel. While foam concrete is suitable for walls, partitions, and non-structural elements, it may not be suitable for supporting heavy loads or multi-story structures without additional reinforcement. Engineers and architects must carefully evaluate structural requirements and consider alternative solutions for load-bearing components in foam concrete houses to ensure structural stability and safety. Moisture absorption. Although foam concrete offers excellent thermal insulation, it is susceptible to moisture absorption under certain conditions. Prolonged exposure to moisture or water infiltration can compromise the integrity of foam concrete, leading to structural deterioration and potential mold or mildew growth. Proper waterproofing measures and moisture management strategies are essential to mitigate the risk of moisture-related issues in foam concrete houses. Additionally, regular maintenance and inspections are necessary to detect and address any signs of moisture damage promptly. Day 6. Fixture installation and finishing touches. The final day of construction is dedicated to bringing the house to fruition. Sanitary ware and kitchen elements are meticulously fitted, optimizing functionality and convenience for occupants. Trimmings and boarding accentuate architectural features, elevating the visual appeal of the interiors. A final waterproofing coating ensures comprehensive protection against the elements, reinforcing the durability of the structure for years to come. Limited design flexibility. Foam concrete may have limitations in terms of design flexibility compared to other building materials. Its lightweight nature and specific structural characteristics may impose constraints on architectural design elements and construction techniques. While foam concrete can be molded into various shapes and sizes, intricate or complex designs may require additional reinforcement or alternative materials. Homeowners seeking unique or unconventional architectural features may need to explore creative solutions or consider hybrid construction methods to achieve their desired design aesthetic while leveraging the benefits of foam concrete. XBlocs are a type of concrete blocks used for coastal protection and wave energy dissipation. To produce the XBlocs, a mold was constructed to shape the concrete into the desired XBlock shape. The mold was made of steel and was designed to withstand the pressure of the concrete. Next, a concrete mix was prepared using high-strength concrete with a low water-to-cement ratio. The mix was then poured into the mold, which was vibrated to ensure that the concrete was evenly distributed and compacted. Once the concrete had set, the XBlocs were removed from the mold and allowed to cure. The XBlocs were then transported to the Calais port, where they were installed along the breakwater. The blocks were arranged in a specific pattern that would provide maximum wave energy dissipation and coastal protection. This video shows the wall production stages in Tachydomi Sa factory. Precast walls have revolutionized the construction industry with their efficiency, durability, and versatility. Their manufacturing process involves several stages. In this guide, we will delve into the step-by-step construction stages of precast walls, from plotting to storing, highlighting key aspects of each phase. Plotting the wall element. The process begins with meticulously plotting the dimensions and design of the wall element. Engineers and architects collaborate to translate blueprints and designs into precise measurements, ensuring accuracy in the final product. Advanced software tools aid in this stage, allowing for virtual simulations and adjustments before production commences. Molding and placing electric water installations. Once the plotting phase is complete, the molding process begins. Molds made of steel are prepared based on the plotted dimensions. Prior to casting, electric and water installations are strategically placed within the mold. This includes conduits for electrical wiring, plumbing pipes, and any other necessary utilities. Careful placement of these installations is crucial to ensure compatibility with the final structure and facilitate efficient installation during on-site assembly. Inserting reinforcement, ironing. Reinforcement is essential for enhancing the strength and durability of precast walls, especially in areas prone to structural stress. Ironing, or the insertion of reinforcement bars, rebar, is a critical stage in the construction process. Rebar is strategically positioned within the mold according to engineering specifications, providing structural support and reinforcement against external forces such as wind, seismic activity, and impact. Proper placement and alignment of reinforcement ensure uniform strength distribution throughout the precast wall. Concrete filling. With the mold prepared and reinforcement in place, the next stage involves pouring concrete into the mold. High-quality concrete mixtures, tailored to meet specific structural requirements, are used for casting precast walls. The concrete filling process requires precision and attention to detail to avoid air pockets, voids, or uneven distribution, which could compromise the integrity of the final product. Vibrators were employed to facilitate the flow of concrete and eliminate trapped air, ensuring a homogeneous mixture and optimal structural performance. Vibration and rotation. Double wall formation. Following concrete filling, vibration and rotation techniques are employed to enhance the consolidation and compaction of the material. Vibrators are applied to the mold to eliminate air bubbles and ensure proper bonding between the concrete and reinforcement. Additionally, rotational methods may be utilized to facilitate the formation of double walls, where two precast panels are cast simultaneously with a cavity between them. This cavity can serve various purposes, such as insulation, soundproofing, or accommodating additional utilities, depending on project requirements. Storing the walls. Once the precast walls are cast and cured to achieve the desired strength, they undergo a curing process before being stored. Proper curing is essential for optimizing the concrete properties and durability. Precast walls are typically stored in a controlled environment, such as a warehouse or casting yard, where conditions are regulated to facilitate curing without compromising quality. During storage, measures are taken to protect the walls from environmental factors such as moisture, temperature fluctuations, and physical damage, ensuring they remain in pristine condition until ready for transportation and installation. Concrete recycling is an important process that helps to conserve natural resources and protect the environment. The Swabian Alb region in Germany is known for its limestone, which is the foundation of the area. However, local construction firms are rapidly depleting this resource, and many are turning to recycling old concrete to meet the growing demand for construction materials. The use of recycled concrete has many benefits. First, it reduces the need to mine for new aggregates, which is a major cause of environmental degradation. Second, it reduces the amount of waste generated by construction projects. Finally, it is a cost-effective way to produce high-quality building materials. Recycling centers like the one operated by the Erdbau company in Kirchheim Tech are helping to drive the transition to sustainable construction practices. These facilities process a variety of concrete and building rubble materials for reuse. The rubble is collected from within a radius of 15 to 20 kilometers from the recycling plant and sorted according to type. Only pure concrete is sent to the crusher, and a magnetic belt removes any steel reinforcements. The resulting product is a clean fraction with a size of 2 to 16 millimeters that can be used as a replacement for gravel from quarries or pits. The recycled concrete is then used to produce fresh concrete for construction projects. The Winnender Frischbeton concrete manufacturer is just one of many local companies that use the recyclate for this purpose. One of the advantages of using recycled concrete is that it is just as easy to use as conventional concrete. It has the same viscosity and is just as resilient. However, there are guidelines that must be followed to ensure that the recycled concrete meets industry quality standards and technical demands. For example, the strength class of the recycled concrete must be at least C2037.